Good morning. Well, this week in physics, our goal is to really work with these kinematic equations and gain a deeper level of understanding of what's happening and how to use those in different situations. And we'll also apply them to free fall problems like we started to last week, but we'll get into a bit more depth. My video this morning is going to focus on how to analyze free fall problems that you're going to face this week, and it'll be really useful to watch before you attempt to do the lab. So let's take a look over here at my doc cam. So what we're looking at here is a sort of a motion diagram of a path that a projectile might take when an object is thrown into the air, like we're going to do with the tennis balls this week. So we have the ground here, and then you have to imagine there's a person throwing an object straight up into the air. Kind of starts to curve, so it's not straight up, but that's okay. And then it comes back down to the ground. And what we're going to do here is I'm going to teach you about a few things that you're always going to know for kinematic problems when we have a free fall situation. So if I write down here, I have some initial velocity vector that is pointing up, the velocity that the ball leaves the person's hand. At the bottom, I have some final velocity vector, and the direction of that vector is obviously going to be down. The first kind of key thing to say here about this motion is that we have something called symmetry, where the initial velocity that it leaves your hand is going to be exactly equal to the final velocity when it returns back to the ground. So what that means is, let's say I throw a ball upwards with a velocity of 5 meters per second up. It doesn't matter how high it goes or any of that stuff. When it returns back to its starting elevation, it's going to have a velocity of 5 meters per second, but it's going to be down in this case. So we're always going to be able to have that kind of piece of information, even if we're not told it specifically in the problem. Another piece of information that we're always going to know for these sorts of free fall problems is that acceleration is always going to be negative 9.8 meters per second squared. So if there's no jets, rockets, strings, anything touching the object as it's in the air, its acceleration is always going to be negative 9.8 meters per second squared. Even if it's moving horizontally, as we get into two-dimensional kinematics, you'll find that the motion in the horizontal dimension up here has no impact on the motion in the vertical dimension. We can treat those separately. Another really critical piece of information is the ability to break the motion into parts. What I mean by that is we can examine just the upward part of this motion, and if I forget for a moment about the second part where the ball comes back down and just look at the motion of the ball going up, I can say a couple important things. And the key here is something happens at this point where the ball reaches the top of its vertical path. You know, if we're thinking about velocity and time graphs, and position time graphs from the previous week, the acceleration vector is the same. If I asked you, what's acceleration here, 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 or here, it's all going to be negative 9.8 because acceleration is a constant value. Velocity, however, is going to be different. I'm slowing, 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 and eventually at the top, I reach a point where my velocity instantaneous at this spot is going to be 0 for a split second. And if that's true, has to be, you know, as my vector changes direction and starts pointing down, we can now know another piece of information to solve free fall problems. Now, as we've talked about, to solve a kinematics problem, we have to have 3 of the 5 kinematic variables. So let's list them out. There's initial velocity, final velocity, acceleration, time, and then displacement. And for vertical motion, we'll write our change in y instead of our delta x, just since we're going straight up, straight down. So let's say I'm doing this tennis ball throw experiment, and we don't know the initial velocity. We do know the final velocity if we break the motion in half. We do know, so that's going to be 0. And we do know acceleration is negative 9.8 meters per second squared. And we are going to know our time value. We're going to measure this in the experiment. So as we throw the ball up, we start the stopwatch, and we stop it when it hits the ground. But there's a really key thing that you got to remember to do. If you break this motion into 2 parts, you know, doing that trick where now we know final velocity at the top is 0, well, we also have to break our time in half too. You see, if we measured a total hang time to do this motion, that value needs to be divided in half, and then we're just looking at this first part of the motion up here. So what I'm saying is, if you ever break vertical motion into parts like I'm showing you how to do, make sure you divide this measured time by 2. And then we know 3 things. We still don't know how high it went, but we have a super accurate acceleration value, a super accurate final velocity value, and our only source of error will be our time measurement. And so we want to do a few trials to get an accurate time, and then we can figure out what we want to know. We can go back and look at those equations of kinematics that I presented last week, and we can select an equation based on what we're looking for. So I could go 2 ways in this problem. I could solve for the initial velocity that the ball leaves the hand with, or I could solve for the maximum height. And once again, remembering that this motion, any horizontal motion, isn't going to affect what's happening in the vertical dimension. So the fact that the ball might not go perfectly straight up and down doesn't matter. Okay? You'll just have to trust me on that one for now. And then, so I can solve those, and that's the 5 kinematic variables, and we can totally describe this motion as long as we're able to measure a hang time, which should be pretty straightforward. So like I said, when you do this experiment, you're going to want to get an average time value to do your calculations with, and then I'll be looking for you applying these kinematic equations to this physical situation. Alright, so in conclusion, some of the key things here from this video were the fact that initial velocity is going to equal final velocity. The way up equals the way down. Velocity at the top is 0. Acceleration is always negative 9.8. Another thing I might add as well is time on the way up equals time on the way down, which kind of follows from this first conclusion. And that will help you immensely when you are looking at free fall problems, because typically you're not going to be told acceleration and you're not going to be told final velocity. You have to, you know, they're going to assume that you know that stuff. And so when you read a problem and you're like, oh, I don't have enough information, you're going to have to infer something. Now, one final point I want to make here. This final velocity is always the velocity right before it hits the ground. after we have a collision with the ground, we'll have to turn to momentum in order to understand the motion of that ball. So for these sorts of problems, the final velocity is right before impact. All right, send me your questions if you have them. Good luck.